Everybody. So today it's my pleasure to introduce Danilo Liarte. Danilo is presently a young researcher founded by FAPESP here at IFT. He finished his PhD at USP in 2011. Then he continued in USP for a postdoc for 3 years, and then he moved to Cornell University for 6 years. And now he's here with us. And thank you very much for accepting our invitation. And today the lecture of this series postdoc on the spot, so make questions please, the title is Universality in Disordered Systems, Jamming and Strange Quantum Liquids. Thank you very much, Danilo.
Thank you so much, George. It's truly an honor to give this colloquium today. And you know, some months ago, I was going out for lunch, and I met George on the way, and he mentioned to me this seminar series that he was starting, and I, of course, accepted immediately, very excited about talking about my research here, being a young researcher and all. And then I remembered then, back in the day when I was a graduate student, I was at USP, as George mentioned, and he gave a seminar. I think it was one of those Convitia Física seminar that they have in USP, organized by the Department of Mathematical Physics, and it was on black holes, and I still remember the punchline. It was like, there are good evidences that black holes exist. And there is one at the center of the galaxy. So when I thought about that, I started getting the butterflies. You know, the standards are too high for this guy. And also, when my colleagues started giving their colloquia here, it just got worse. So if you don't do something good, at least you can aim at doing something good. That's my hope that you indulge me for my presentation here. So let me start here with a quote that I believe many of you might know, at least some version of it, and this is by Leo Tolstoy. People might know it as the Anna Karenina principle, and it says, all happy families are alike, and each unhappy family is unhappy in its own way. So the idea is very simple, you know, right? To be a happy family, you have to agree about lots of things. You have to agree about, say, how you spend money, if you have children or not, or I don't know, maybe religion or something like that. And you break one of those ingredients and you get an unhappy family, and it's unhappy in its own way. You know, there are many examples or many versions of this quote, and I like some of them. And you might be led to think that there is something similar going on for ordered systems, for instance. You might think that all ordered systems, or at least some classes of ordered systems, are alike, and each disordered system is disordered in its own way. And one of my goals today is to give you indications that this is not always the case, and that there is some sort of universality concerning disordered system, that you might find some unifying framework to describe lots of different disordered systems. So that's the main idea. And I'm going to start with an example that's an example that I'm familiar with, and I started graduate school working on problems like this. And this is encapsulated by this term, complex systems, which is it's kind of silly when you try to define what a complex system is, but that doesn't matter. You can define it by the set of elements that you have there. You can have, for instance, spin glasses. This is one example of a complex system, and people have, for instance, econophysics, and evolution, game theory, neural network. There are many different complex systems. And some of you might remember that not long ago, 2 years ago, this gentleman here, George Parisi, received his Nobel Prize for his contribution. This is my paraphrasing the Nobel line, for his contributions on complex systems. I'm very familiar with Parisi's work, particularly on spin glasses. And I'm going to speak a little bit more about this and try to explain why I believe it became so important. Because, you know, spin glasses, concerns a set of magnetic alloys, disordered magnetic alloys. And why do you care so much about spin glasses at all? And the idea is that the framework that he developed ended up being important for lots of different systems, and that's the idea behind this general thing here. So there are two secret ingredients, for instance, if you want to describe a spin glass, and these are quench disorder and frustration. It's very simple to explain what disorder is, for instance. You imagine in those systems you have, for instance, collections of spins. You might take them to be Heisenberg spins, or they might be Eisen spins, so that they point just on one direction. They might be point upwards or downwards. And then they interact so that if this is blue, for instance, they like to be parallel, pointing in the same direction. And if those are red, they like to be anti-parallel. So there are ferromagnetic, competition between ferromagnetic and anti-ferromagnetic interactions. So this, in principle, for a spin glass is disordered. There is a random variable associated with those interactions. And this gives rise to this spin glass phase where the spins are frozen, but in some disordered configuration. Now, the second ingredient that I'm mentioning here is frustration, and it's easier to put this in a triangular lattice just to explain, but you don't need to have a triangular lattice to talk about frustration. And here the idea is very simple again. For instance, suppose that those two spins at the bottom here like to be anti-parallel. They have an anti-ferromagnetic bond, and they have ferromagnetic bonds here to a third spin. So if this spin here agrees with this other spin here, he's not going to agree with this second spin at the bottom. So there is some frustration there. And when you combine these two ingredients, disorder and frustration, you get something like a spin glass phase. And what made this whole field of complex systems so popular and so widespread was the fact that many different systems have these two ingredients. And if you devise some theoretical framework to describe spin glass, maybe you can just describe something like econophysics or game theory or something like that. So that's one of the main motivations. Now, these are spin glasses, and back in the day, there was this hope that you could use something like a spin glass model to try to understand structural glasses. And here I'm giving an example of a structural glass. And very quickly, people realized that this was really not the case. I mean, the structural glasses were different in important ways. One of them is that, for instance, this disorder here is self-generated. And by this, I mean, the disorder is on the degrees of freedoms, the positions that you want to describe, for instance, using statistical mechanics. Whereas here, the disorder is separated from the spin degrees of freedom, for instance. That's one of the reasons why these things are so different. And you know, glasses is a hard problem. The glass transition, understanding the glass transition is a hard problem. As many of you probably know, if I had lots of money, I would probably fund someone to really come up with good ideas to understand and to explain glasses in a general way. And unfortunately, I don't have lots of money, but Jim Simons has. And he has, for instance, a foundation that funds lots of very beautiful enterprises. And one of them, there is a Simons collaboration on cracking the glass problem. And they have made some amazing contribution through many years. They've been working on very different systems, and one of the most important contributions that they have been doing is on this field of jamming, which I'm going to spend a few more. I'm going to talk about for the next slides. Yes, go ahead.
What do you mean by glass problem? What's the problem exactly?
Well, there is a glass transition. You know, glasses. When you talk about glasses, there are very many different open problems regarding them. They are not stable states of matter. So there is a sense in which you can associate the glass transition to the behavior, to the dynamic behavior of glasses, but that's not fully understood, for instance. And then there are many open bifurcations or many other problems, satellite problems concerning this, and that's more or less the idea. So let me talk about jamming. And I'm going to start with a very simple example. Suppose you have a collection of disks in a plane. You can easily generalize this to higher dimension, but for the moment, it's just simpler and more convenient to draw this in a plane, and they interact only via excluded volume interaction, so they don't cross each other. And if you start compressing the system, what do you expect what do you expect to happen? Well, at some point, they will jam, and because the set of disks is not uniform, you have different sizes here for these disks, they form this disordered contact network that resists compression. Now, usually you describe this transition in terms of an elasticity, an elastic theory, and you look, for instance, into elastic moduli. Right, when you ramp up the compression, as you reach this critical point, the bulk modulus jumps to a finite value, whereas the shear modulus grows continuously from 0. And this happens right at some critical coordination number for this disordered network. And just to remind you, I don't expect everyone to know this terminology here, but you know you associated a bulk modulus that's an energy constant associated with bulk deformations that involve changes in volume. And the shear modulus is associated with shear deformations that are deformations that do not involve changes in volume. So the bulk modulus jumps and the shear modulus grows continuously from 0. There are many important properties regarding this jamming transition, and I'm going to over some of them. One of them is that if you add a few more bonds, or if you compress the system a little further, you have this population of low energy excitations in the system. And here I'm giving one example of one of these low frequency soft modes. It's very hard to see here that there are some dots there representing the particles, and the lines are the polarization of the particles, so they want to move on this or that direction. So it's a kind of a disordered low frequency soft mode. It costs very little energy. And this happens because you have a network that's marginally stable. It's just on the verge of having stability, of being mechanically stable. So you can look into this and describe this jamming transition. As you get close to this jamming transition, if you look at the density of states, for instance, at lower frequency, you have this enhancement of the population of these low frequency modes. So this is yes, go ahead, Nita. So you can, for instance, write down some elastic.
Definition of bulk and shear modulus.
Yeah, yes. So you describe, for instance, an elastic material in terms of an elastic free energy, which is.
For this example of the disks.
You apply some compression, for instance, you have some energy cost associated with the compression. The energy term associated with the compression is proportional to the bulk modulus.
I'm sorry,
The energy term.
I'm sorry, I just have these disks don't interact. They just either touch or don't touch.
Yes.
What's the energy?
If you keep compressing, they can rearrange. So there is an effective interaction. There is a gradient term. You can go from this microscopic model into an elastic continuous model. In the elastic continuous model, you have some cost, some free energy cost to compress it as you keep compressing it. Even though you start with a model that's microscopic, that only have excluded volume interactions, you can derive some elastic free energy for it. And the elastic free energy will penalize it if you try to do some kind of bulk compressions. If you try to compress it, you have to pay some energy to it.
I'm sorry, I just don't know what you mean energy. I have a density of these things, but what's the energy? I don't. If there's no forces between them, what's the?
There
energy?
are forces.
I thought you said it was just exclusion.
Yeah,
So how do I, that's not a continuum.
but they are forced. And then you can coarse grain this and get a continuous elastic energy, right? You're thinking only on some microscopic elastic module, but to go to the elasticity theory, you have to take the continuum limit.
I see, okay, so that's the part I'm missing. Okay.
Yeah.
So these are only well defined in the continuum limit, is that right?
The elastic moduli are defined only for the continuum limit, for the field theory.
Okay.
But yeah, in principle, yeah. I'll get to another example that's mass spring systems that, anyway, we'll go there. So here we go. So there is this density of states and this enhanced population of low energy, low frequency modes here. And at some point, there is a crossover here to the Debye behavior, if you're familiar with it. If you're not, it's not so important. But this crossover gets pushed down to lower and lower frequencies as you go closer and closer to this jamming point. So this is one of the trademarks. And I'm emphasizing this because I'm going to connect to this when I talk later about strange metals, for instance. And another aspect, or this is also reflected, for instance, in measurements of the structure factor. You know, you can measure the structure factor using scattering, and measurements of the structure factor shows this rounded maximum here at some characteristic frequency. And I'm going back to this. Go ahead.
This phase transition that you show has a second order and first order phase transition. Is always like this, or this specific phase transition, this jamming phase transition?
Is specific in what sense? It's always like this. In what sense? Like there is a sense in which there are other systems which also show the same kind of behavior, and I'm gonna get to that. But
yes. So my question is just this diagram that you show with the two phase
Yeah.
transitions, the bulk modulus and shear modulus.
yeah.
This is what you mean by jamming, right?
Yes.
Okay. So
Yes.
that's
Yes. So jamming has all these interesting features, and I've been talking about jamming of spheres, for instance. But the important feature that I'd like to emphasize about jamming is that it's kind of universal, and that's the main idea. And even though you have devised some theoretical treatment for spheres, the same kind of ideas also appear, for instance, if you study confluent cell tissues. And these confluent cell tissues are like the cell tissues you have, for instance, in your skin. They are confluent because there are no gaps between the cells. And what we see here is that there are some empirical Hamiltonian that you can write down for this kind of system. And there are two terms here, one that gives a target area for each cell, for instance, if you're dealing in 2 dimensions, and a target perimeter for each cell. And depending on the relationship between this area, this target area, and this target perimeter, you can have the formation of structures that are more rounded or more elongated. And these different structures will behave differently. Some of them, if you are in this limit here, where the perimeter is more important, you get something more like a fluid phase. And if you are in this regime here, where the cells are more rounded, you get something like a solid phase. And there is a transition there in between that's much like a jamming transition. And people have realized that there are many aspects of the jamming transition that can be incorporated in these confluent cell tissues studies. And then, for instance, there is another.
Danilo,
go
sorry,
ahead.
I lost. What's A and what's P?
A is an area.
Okay.
So here is a sum over the. These are just the areas are like springs, but the area of cell I minus some target area A naught. Okay. And this is the perimeter, of each cell. And depending on this, the relationship, you can derive or write down a dimensionless ratio between, for instance, perimeter and the square root of area, and this would give you a dimensionless parameter that you can control to hit this fluid or solid phase, for instance.
If I understand, this answers Nathan's question in principle, right? What's
This is
the
one of
energy?
the systems that would have, for instance, this is one of the systems that would have an elastic energy very clearly from the start. And
I see. I understand.
there are others,
Okay.
but even in the Gemini of spheres, you can come up with something that would be a continuum theory and so on. Yeah. There's machine learning. Machine learning is very popular these days, and you can make some mapping between, for instance, the error landscape of neural networks, and this turn out to be analogous to the complex energy landscapes of systems near jamming. So there is, in some cases, you can even write down the mapping very clearly. For instance, this started with the study, for instance, of perceptron models and things like that. So you can also use the same kind of technology that is used, or the same kind of structure that is used to understand jamming, to understand some of the properties in machine learning. And then there is strange methods, which I'm going to go into more details by the end of this talk. And the main point here is that jamming, like the spin glass was kind of a proxy for several different complex systems, jamming serves as a kind of a proxy for many different disordered elastic systems. So that's one of the main ideas here. And that's one of the reasons why I believe that jamming is very important. Now this transition is kind of funny, right? If Paul Ehrenfest was alive today, he would be very confused in classifying this as a first order or a second order transition. One modulus jumps and the other grows continuously. So that's not important. That just makes it funny. But there's another system that's very much like jamming, but with some important differences. And this is what we call rigidity percolation. So I'm going to introduce rigidity percolation here. And you can start with a very simple lattice model, for instance, a triangular lattice, where you only have masses and springs connecting the masses. Very simple system. And you can imagine that in this case of a triangular lattice, this is a rigid object, right? If you try to deform it, it's going to resist the deformation. And there's no way. I mean, each side here has lots of different connections, so it's rigid. But you can imagine that you start randomly removing bonds on this triangular lattice. And what happens when you randomly remove these bonds is that you get a transition that's much like jamming in some sense. The bulk modulus and the shear modulus go continuously to 0 at some critical coordination number here, or some critical average coordination number. But unlike jamming here, you have something that's clearly second order. All the moduli go continuously to 0. And so Paul Ehrenfest is much happier now because it's easier to classify. Now, I like this kind of model, this rigidity percolation model, for several reasons. One of the reasons is that they are easy, or if they're not easy, they are at least easier to simulate. They are amenable to analytical calculations, and there are some approximations that I'm going to explore that make it very simple to extract information, analytical information about these systems, even for this disordered network that I'm showing here. But then, unlike the jamming transition, they don't show a jump for the bulk modulus. So that's something that's kind of different. And that might lead you to ask whether or not there is some sort of unifying framework that would describe both the jamming and the rigidity percolation transition. And as it turns out, there is, and we've devised it. And I'm going to explain this to you. But before I explain this sort of model, let me just thank my many collaborators in this area, because from now on, I'm going to talk about research that we've developed throughout the past couple of years. So you can see the faint lines there. Maybe you can. There are some faint blue lines and faint red lines there. And then some dark lines. What we have here is a combination of two lattices. There is a honeycomb lattice here shown in blue. Maybe if you if you squint a little bit, you will see there are some blue letters here, honeycomb letters. And then in red, there is a triangular lattice. The honeycomb lattice has a finite bulk modulus, has a B greater than 0, and a 0 shear modulus. And what I'm going to do, I'm going to populate each bond with a spring with some probability, PB here, which for this figure is just 0.9. And the triangular lattice has finite bulk and shear moduli. And I'm populating each bond with a probability Pn here. Now it's very easy to calculate, for instance, the average coordination number for this combined lattice, this combined disordered lattice, and that's just given by this formula. And what you get here is that if this average coordination number is smaller than a critical value, a critical coordination number, ZC here, you have a floppy state. Go ahead, Ricardo. Yeah, exactly. It's 0 energy cost to apply a shear, yeah. Yeah, exactly right, yeah.
Why is it not a triangle?
So let me come back. You mean you can write another, you mean this side here?
No, just go a little bit up.
Yeah.
Now go northwest.
Northwest, like this? This guy?
Yeah. So, for example, if I go south,
I go,
connect to that.
because I'm assigning a probability distribution for each bond. So there is a probability distribution. A bond is populated with probability Pn, for instance, for this lattice. It's randomly chosen. Well, I mean, you can devise a model. You are asking about the general, if there is a physical system that naturally gets this structure, or if I can just assign a lattice where I put a bond with a probability. There is a defect. It is a disordered network structure, right? So I mean, I can define the lattice this way. There are some systems, these will mimic some disordered elastic network in general. But this lattice, defined this way, I can calculate almost everything for it. It is not a crystalline lattice in the sense that it's not periodic, it's a network. Yeah. So we were here. So if average C is smaller than ZC, you have a flop state. If average C is greater than ZC, you have some rigid elastic state. Now this is C here. There is a very simple counting argument that you can use to calculate, for instance, or to calculate this critical coordination number here that was given by Maxwell a long time ago. And it's just 2 times the dimension. So you can just count, for instance, degrees of freedom and number of constraints, and you find out that this is the isostatic point where this transition happens. Now the important thing here that I'm not going to give you all the details is that you can map this diluted network system into a homogeneous system, an effective medium system that you can solve analytically by the end of the day. And this map goes by the name of CPA. It's coherent potential approximation. It doesn't mean much, but anyway, there is this map that you can use, and by the end of the day, what you get are effective spring constants, KB and KN, that will, in general, depend on these probabilities, PB and PN, and potentially also on some frequency, omega, if you are driving your system with a certain frequency. Yes?
So are you assuming a 2-dimensional model everywhere, or this is just a graph, but you are applying for a any dimensionality.
So I can calculate this for this particular model in 2 dimensions. I can also calculate it for a model in 3 dimensions. I have the analogs of this kind of model for 2 dimensions in 3 dimensions. We will use, for instance, the diamond lattice and a combination of a diamond and an FCC lattice. I could give you more details if you want, but anyway. There are generalizations for higher dimension, and there are generalizations also for disordered, when you start with a disordered structure from the beginning. So,
and the results are qualitatively
they are the same,
different?
essentially.
Are the same, essentially the same.
The universal scaling is going to be the same.
Okay.
Yeah.
Okay.
So by the end of the day, you get solutions for these effective spring constants, and from the solutions, you can calculate the elastic moduli. You check the hydrodynamic limit. That's what I was telling Nathan earlier. You take some continuum limit and calculate the elastic moduli, and you can draw phase diagrams and calculate all the properties that you might be interested for this system. And you might, for instance, draw a phase diagram here. This is in terms of PB and PN. And here I have a rigid phase here, where both moduli are greater than 0. A floppy phase where both moduli are equal to 0. There is a rigidity percolation line. From there, the moduli grow continuously from 0. And terminating this rigidity percolation line is a jamming point. And in the jamming point, you have a bulk modulus finite and a shear modulus that's 0. So we have this unifying picture for both jamming and rigidity percolation, and the jamming point works as a kind of, for the specialists in statistical mechanics, as a kind of multi-critical point in this case.
Sorry, there's some randomness in this, right? Because PB doesn't tell you which bonds I break, right?
PB is the probability of assigning a bond for the honeycomb lattice.
Right, but
yes.
it's random. It's
random,
chosen.
yeah. Yeah.
So how can you get? So isn't there some error? I mean, there's an error bar, right? It's not. You can't get, depending on how you choose PB, depending on which bonds you break, doesn't it give you a different answer?
In a real system, if you do a simulation, for instance, there is an error bar, and really, there are other subtleties. For instance, there are some regions that are over-constrained, regions that are under-constrained. There is all of that. But this is an analytical theory, some effect median theory, and in this theory, there is no error bar. The moduli go right to 0 there.
So you can claim you theoretically can compute that.
Yes.
I see. Okay.
Yeah. And of course, it's an approximation, but yeah, it's a good approximation for all purposes. It gives you the...
Sorry, just to understand. If I do computer simulations, I'm going to get a whole bunch of error bars, right?
Yes.
So which of those are you computing analytically? If you have an error bar, how can you...
No, I'm not computing the error bars. The line is analytic. This transition line here is analytic.
Yeah, but it's the answer to what question? That's what I'm curious about. Because there is no question, because the question has an error bar in it, right? Because it's random. There's a randomness.
I'm not sure if I'm following.
So if somebody gives you a lattice,
yeah.
a network, and tells you what the network is, then you can compute a number associated to that network.
Yeah.
But PB doesn't tell you what the network is. It just tells you some property of the network, right? It says
yeah.
half of the bonds are broken. Somewhere.
Yes, exactly.
It doesn't tell you which bonds are broken.
Exactly, yeah.
So depending on which bonds I break, I would get a different number.
That's right, yeah.
And which of those numbers does the analytic computation give you?
No. There's something, for instance, there's a concept that I'm going to borrow here from spin glass literature. There's something that's called the, what's the name again? The point is that, of course, you have a distribution associated with this disorder, right?
Yes.
And for almost all cases, all instances of these disordered configurations, you get a certain macroscopic quantity for all but a set of 0 measure. Okay. So almost every, I mean, that's something that people, that's a self-averaging property that people talk about in spin glasses that is very common in systems with quantity disorder. For almost all of the instances, the typical number, the average number will be the same as a typical number. That's the main idea.
I follow up Nathan's question. So if you make the simulation with an infinite number of if the simulation takes into account an infinite number of individuals of the randomly chosen, are you going to reach to this line with 0 error bars? So my question is, okay, let's assume that we make this simulation with an infinite number of individuals.
I believe the arrow is going to scale and it's going to vanish with the number. As you check the thermodynamic limit, it's going to vanish. And
obtain your line?
Yes, probably. Yeah, though, I mean, I cannot, there is no proof of that.
Okay.
There's no mathematical proof of that. But there are some approximations involved here that I'm not going to discuss. And everything, I mean, there's no mathematical proof. That's the answer, essentially.
So may I guess that these error bars comes because every simulation, numerical simulation, assumes a finite number of...
Partly, yes, for a finite system, yes. Partly it's finite size, yeah.
So thank you again. Just to review a little bit, we start from different lattices, triangular and hexagonal, with these two probabilities.
Yep.
And you do theory.
Yep.
And then you show this phase diagram. You not talk about computer simulation at this moment.
No. Mm-hmm.
And when you have ZC, it's the crossover or the critical point. What is the point that the jam happens? This is the point where you have the
ZC marks the point where rigidity happens, where it becomes rigid.
Rigid. Oh.
So in all this line here, average Z is equal to ZC. That's this line.
Okay.
Which is given essentially by one of the slides that I showed you earlier, by this formula here. So this equals 2D is that line.
I saw.
Yeah.
I also have a question. So
yes.
On this system, what does it mean to be fluid or to be rigid? Because I don't see what's moving.
It's rigid. If you apply some deformation on it, it's going to cost energy. Okay. For instance, it might cost compression energy. Remember, this is a mass spring system. If you have something like this, I can give you a very simple example with a square. So this is just a mass spring system. And this, it costs 0 energy to do this, for instance, to shear it. It costs energy to try to compress it, because I'm going to change the lengths of the springs, but it costs 0 energy to shear it. Of course, if I put one extra bond here, then it costs energy even to shear, because I'm going to deform this bond. So, yeah.
Okay, thanks.
One thing that isn't clear to me is that is B a global property? Because you told about the square example.
Yeah.
And
B
is a measure of like the whole lattice, or just a little?
It is the whole lattice. It is the whole
okay.
lattice. What we do in general is that you apply some pressure, for instance, at the boundaries of the systems, and this is, of course, propagated in the lattice, but that's the usual way. Or you apply some shear at the boundaries of the system.
Okay,
that's a global property, yes.
So is it easy to understand why the phases are only depending on these probabilities and not on the spring constants? Correct me if I'm wrong, but I understood that there is a spring constant.
I have to explain. I didn't give you all the details, but I can explain it more than it become clear. Okay. The original model is for a diluted network with fixed spring constants. You can say spring constant is equals to 1.
Oh,
And
okay.
the
So that's
model
why
is
this-
disordered.
Okay, okay.
And then you map this into a homogeneous network with effective spring constants that will depend on these probabilities.
Okay, okay.
Okay? Yeah, I mean, I have limited, yeah, I didn't explain all of this. All right, so I told you about this phase diagram, and you end up at a jamming point, and you can ask, I told you about the boson peak at the beginning of my talk when I talked about jamming, and you can ask whether or not this kind of network structures would have also a boson peak. And of course, as you get close to this jamming point, and the answer is yes, you can plot the density of states as a function of frequency. And in fact, you have some enhancement of the population of low energy modes here associated with this boson peak. And that's much like what you have for jamming of spheres. Now, you can also ask about the universal scaling behavior of this system. Is that the same universal scaling behavior that you would expect for systems near jamming? So let me take show a few slides trying to go over a very quick introduction about scaling behavior in the context of statistical mechanics. And I'm going to skip this story here on the interest of time. And you all know these guys. At least Ken Wilson is a high-energy guy, so you probably are very familiar with him. And these guys were mostly responsible for much of what we know about the renormalization group today. And renormalization group in the context of statistical mechanics gave a very fundamental understanding of phase transitions and critical phenomena in general. So one of the central ideas is that in the renormalization groups is that of scaling variance, and I can give you very simple examples. For instance, for magnetic systems, showing this scaling invariance. Imagine that you have some Ising system, magnetic systems with spins, and spins might be pointing up, for instance, these black dots here, or down, which would be the white points here. And if you are above the critical temperature, you have a configuration like this. And you might imagine doing some sort of coarse graining in this system, dividing this system into blocks, and then assigning new spins for each of the blocks. The rule for which you assign these spins doesn't matter much. You can do something like the majority rule or the decimation rule. It doesn't matter. But you can create this new block spin system and rescale so that it looks like the original figure. And if you do that, for, above the critical temperature, you get a figure like this. And if you pay close attention, you'll see that it's much more granular than the original figure. If you keep doing it, it gets more and more granular as you keep doing this coarse graining and rescaling. And this is not scaling invariant. But if you are at the critical point, right at TC, and you do the same analysis and the same protocol, you keep getting the same kind of statistically very similar figures. And that's one of the consequences of scaling invariance in this system. And this is ultimately related to universality in statistical mechanics. So let me come back to this phase diagram here. Now I'm going to show elastic moduli, but now they are frequency dependent, and I'm not going to have time to go over the physics of frequency dependent elastic moduli, but anyway, there is a real part here that is associated with the energy that is stored in the springs, and an imaginary part that's associated with losses. And you can look at the dependency of this on frequency. And the first thing that you'll realize when you stare at a plot like this is that they are in log-log scale, and they all look like the same curve, except they are shifted in this log-log scale. And this is a hint that there is some sort of scaling variance at play there. The idea is that you can rescale G prime and the frequency here to collapse this data. If there is this scaling variance, you can collapse this data by doing this appropriate rescaling. And as it happens, you can do something like that and collapse the data. And you get very nice collapse. And you can even write down something like this for this general universal scaling form here. You rescale the shear modulus by delta p, and as a function of the frequency, rescaled by delta p squared, for instance. This is the distance to the critical point, for instance. You understand this delta p as the distance to the critical point. So you might be familiar, for instance, with an example for magnetic systems, the Ising model. You have something, a phase diagram in terms of magnetic field and temperature, and the first order transition line that ends at a critical point there. And you can find something that is very similar here for the magnetization as a function of field and temperature. There is an overall power law here, times some universal scaling function of this invariant scaling combination. So this might be familiar, and one of the guys who did a lot of work on this came up with these ansatz. You can start with something like a free energy. This delta here might be the distance to the critical point, for instance, Tc minus T. So you can write some ansatz for the behavior of the free energy in terms of the relevant variables in your system. So there is some power law here and some functions, a universal function of these combinations, just like you have a function here of these combinations. And it's nice because if you do that, you can calculate all other scaling forms by taking derivatives of this free energy, for instance. For instance, you can take the derivative of the free energy on the magnetic field, you get the scaling form for the magnetization, and so on. And you can get lots of results just from this simple scaling analysis. And people have done that. My colleagues called Goodrich and Andrea Liu and Jim Sethna have done the same kind of analysis for jamming, based on some ansatz for the free energy as well, but they didn't have the dynamic behavior. So one of the things that we did was to extend this in order to also to include dynamic behavior in this system. Now, I've shown you this before. You have, in your effective medium system, you get these effective spring constants that in general depend on PB and PN and omega. And you can work out the equations and get some asymptotic solution near the transition for these effective spring constants that will depend in general on some excess contact number frequency. And from this, go ahead, Pablo.
So by dynamic, you mean the frequency, omega is the frequency of vibration modes of the elastic network, right?
Not necessarily. It's the frequency in which you are forcing the system. You have the natural frequency of the lattices, and you might apply some force and do a Fourier transform in time, for instance. It's that frequency that I'm talking about. So you get something like this, and from this, you can calculate something like a susceptibility, a generalized susceptibility. This is a displacement response to a form. This is a general scaling form for this susceptibility. I do not have time to go into the details of this, but there is a power law here and a universal scaling function here in terms of wave vector, rescaled wave vector, and frequency, in this case. And gamma, nu, and z are critical exponents. And this curly L here is supposedly a universal scaling function. Now, with this effect medium theory, I can calculate explicitly what this universal scaling function is, this explicit formula for it. And it's important to notice that in statistical mechanics, it's very usual to focus your attention on calculating better and better numbers for the critical exponents. But there are many quantities which are universal, which are preserved. And maybe it's not proven. There are indications that this scaling function is also universal. So knowing the functional forms for the scaling functions become as important as knowing the critical exponents itself. So of course it's tough, it's difficult, and just in few examples you can do something like learning what the universal scaling functions are, but it is important also, so it's something that's interesting. Go ahead, Nathan. The imaginary part is associated with dissipation. So you have a response, and the response is complex. The real part is associated with the energy stored, and the imaginary part is associated with dissipation. Márcio.
So, just by curiosity, by universality you mean just the functional form, or the exponents are universality itself, in the sense that if I change the network, I got the same exponent?
Yeah. So there is a sense in which there is a fixed point in the randomization group that controls the overall critical behavior of the system, that controls the phase transition. And associated with it, there are the critical exponents, which are universal for lots of different systems in parameter space. You can change many things, and they share the same critical exponents. And also other quantities are also universal. One popular one are the ratio of critical amplitudes, for instance. People talk about this, statistical mechanics. And there is no proof that this function is universal, but it might be. I don't know. There are indications, some simulations that suggest that they are, but yeah. So I'm going to skip this. And the important thing is that I introduced this susceptibility and as the free energy for a system in equilibrium, a quantity like a response function like this, you can extract lots of information from it. You can calculate almost everything. You can calculate elastic moduli. You can calculate viscosities and correlation functions and everything from it. The same way that you had, for instance, based on Widdom's scaling ansatz, you can take derivatives and make simple algebra to calculate the other scaling forms. So this ends up being very general. And in particular, you can calculate the structure factor here, and I'm showing this, and I can even plot, for instance, this universal scaling function for the structure factor. And as you can see here, this is the rescaled frequency, this V here. This is the rescaled momentum, the wave vector, this U here. And there is a rounded maximum here at some characteristic energy, which is emphasized here by this dashed line, which is almost independent of the wave vector. And this is just the boson peak that I mentioned earlier. This is a signature of the boson peak. And this is what makes the connection with the strange metals by the end of the day. And I have just like 2 or 3 minutes to go, so I'll just go quickly over this. You know that there is, I'm showing here the phase diagram for a high TC superconductor, BISCO, and what I'd like to emphasize here is this region, this strange metal phase. It is a metal, though it's a bad metal in some sense, and it's strange in the way that it shows lots of anomalous behavior from what would you expect, for instance, if you applied something like firm liquid theory. And I'm not going to give you details about this, but anyway, the important thing is that you can make some measurements here, and some measurements are very unusual. And here what I'm showing is some response function, just like the response function that I was calculating. But of course, you have to take into account that these are charged systems, so this is a charge density response function and so on. And as in the case of the boson peak here, you have some rounded maximum here at some characteristic energy scale that's almost independent of Q. That triggers some kind of connection between systems near jamming or glassy systems and strange metals. And what we did next was to take this analogy more seriously and try to come up with some extra ingredients in our model to try to interpret these results for strange metals as some sort of proximity to a jamming transition. So that's basically what we did, and I'm not going to give you details. And here is the effect medium theory. Here are the experiments. We have some collaborator who did the experiments, for instance, for the strange metals. And rather than trying to fit the data, really what we wanted to point out is that there are some analogies, and there might be something at play here that is a signature of glassiness or closeness to a jamming-like transition in the strange metals case. So that's basically the main idea of this work. Okay, I'm towards the end of my talk, so I hope I have given indications that jamming is important in this sense that it serves as a kind of a proxy to several different disordered elastic systems, and we've come up with this microscopic, both microscopic and continuum theories and phenomenological theories to describe this jamming transition, and also made contact with some recent measurements for strange metals. Now I collaborate with lots of people, both here in São Paulo and Brazil. William is here, Pablo is there, and my students are there, and also many people, I'm mentioning just a few here from abroad. And if you know, there are some opportunities for master and PhD fellowships from FAPESP if someone you know would be interested in these topics. Okay, thank you very much.
Questions?
Okay, just a simple question, but can you explain a little bit more about the application of jamming to machine learning that you commented? That was
I cannot. I can point you to the right directions. Okay. I mean, there is some, you can derive some error landscape for your neural network, and I cannot give you much details about this, but there is a mapping between this error landscape and what you expect, for instance, for the complex energy landscape in systems near jamming. And the whole thing, I mean, there are satisfiability problems that people talk about, and anyway, I cannot give you much details about this, but I can point you to the right references.
Sure. Yeah. Thank you.
It wasn't clear to me what properties does strange metals behave that are strange. I don't think I
So that, for instance, that rounded maximum there is very different from what you would expect, for instance. And that wave vector independent, that's one of the anomalous behaviors. There are many others associated with conductivity and so on and so on. But that's one of them. You don't expect to have a rounded maximum at some characteristic of frequency there that is independent of the wave vector or something like that. That's
thank you.
Hello. Thank you for the very interesting talks. I have two comments and questions. One is, where does the quantum liquid come here? Are they superfluid?
The strange metal, the strange metal phase, you know there is a firm liquid theory, and you try to apply it for...
But quantum liquid should be superfluid, no?
Say that again?
Quantum liquid should be superfluid.
Yeah.
Is it superfluid in somewhere? I don't understand. Why you call it quantum liquid?
It is a charged quantum liquid, in this case, for instance.
How is quantum
maybe that's a nomenclature that people don't like, but people call strange metals also quantum liquids, right?
Okay. Another comment. When I did PhD maybe 50 years ago, Tom Lubensky was our professor.
Oh, you did at Penn?
Yes.
Okay.
But is he still living?
He is. He's living. He's well. He swims like 4 days per week or something. And
he was our professor 50 years ago.
Yeah.
At Penn.
No, Tom is great. Yeah.
Or this is a very good area to work on. Other questions? Let me ask you, just for curiosity, can you use these ideas to analyze soap bubbles, you know, bolhas de sabão, that when you press them, they just get jammed?
Yeah.
And reach some conclusion about these systems? Have you ever thought of it or somebody?
Yeah. People talk about this. I'm not sure if it would be in the same universality.
Okay.
But it is in general in the same kind of, people talk about bubbles and
Okay.
foam and things like that.
I see.
Like shaving cream and
Okay. Any other questions? So before finishing, I would like to ask Danilo in particular and all postdocs that have helped me with this colloquia, because I know that you did your best, and thank you very much. And I hope that you continue helping and collaborating with the colloquia. Thank you very much, Danilo, and to all postdocs.